All right. So looking at this, we're starting out, the first section will be starting today, finishing up tomorrow, or that's the plan. And you will see in here typically if things kind of extend into the next day, that isn't uncommon for that to happen with AP Calc. There's just kind of some more flexibility that way with this particular class. But we have on here, I've already explained, this first chapter is really looking at or reviewing what you've done with functions in the past, just learning and reviewing those functions so that when we get to finding the derivative and the integral of a function, we are familiar with the functions themselves. And so it has on here, functions arise whenever one quantity depends on another. So I have a couple situations up here. And I should say, with functions, you want to understand 4 representations of functions, and one of those is a verbal representation, so understanding in words what a function is telling you, and that's kind of where this is coming from, comparing the wording of a function and then giving it a formula. But 2 scenarios you might be familiar with. So we have the area A of a circle and the radius R of the circle. Which one depends on the other? So if you have the area of a circle and the radius of a circle, what would you say depends on the other one? Megan?
I'd say the area depends on the radius.
So area depends on radius. I would agree. Typically you have the radius to find the area. So then I have here what rule connects R and A, and that would be the function. So basically, how do you find the area of a circle? Dalton?
Well, I had a question about
okay.
Which one depends on which. Because if we have changed the formula so that it's R equals instead of A equals, would that change which one is depending on the other one?
It would for that scenario. So that would be if you wanted a specific area, so you were trying to find what radius. But typically for a circle, the radius is what's going to determine the area.
So it's just how we generally see the equation written, whatever.
Yes, but certainly it could be rearranged so that if you have an area, you'd be finding a radius. That would fit that, yep. So the rule, though, that we have for connecting radius and area of a circle, so basically the formula for the area of a circle, pi r squared, so A is pi r squared. So looking at that, with each positive number r, there is associated one value of A, and we say that A is a function of r. So area would be a function of the radius, typically. Certainly, functions can be rearranged, like Dalton was just talking about, so that you're kind of switching independent or dependent. You're taking the inverse of the function, if you will. But typically, area, we would say, is dependent on the radius of a circle. And then just another scenario, so if you're looking at human population of the world, P, and then time, T, and that time could be in years, let's say, which one depends on the other? So does population depend on time, or does time depend on population? Population depends on time. Typically in calculus, if one of your 2 variables is representing time, time is usually always independent. So you would say, and there isn't necessarily an explicit rule, you would need information about what population you're talking about, what time period you're talking about to have a rule to compare population and time. So for each value of time t, there'd be a corresponding value of the population p. So we would say that p, population, is a function of time t. And how this is worded when you're saying one quantity is a function of another and really thinking about which one depends on the other, you'll be writing functions and setting up functions, so that's why the wording is important. We'll obviously keep talking about that as we go. So I know this is a lot of fill in the blank, but it's just reviewing vocabulary you've heard before, perhaps, I don't know, looking at it defined maybe in a way that you've seen before or maybe haven't, but just reviewing, like I said, terminology that you should have seen either in pre-calc or before that. So we have how a function is defined, a function f. is a rule that assigns to each element x in a set A exactly one element called f of x in a set B. I realize this can also get very wordy, so don't get overwhelmed with all of the words. I'm going to try to walk us through this. So assigning each element x in a set A, so down here the set A is called the domain of the function. The domain includes all of the x values, which is why x is an element of A. And then we have f of x is an element in a set B, and that would be the range of f is a set of all possible values of f of x. We know f of x represents the y value as x varies throughout the domain. And then a symbol that represents an arbitrary number in the domain of a function f is called an independent variable, while a symbol that represents a number in the range of f is a dependent variable. And then another way, this is just another way to think of domain and independent versus range and dependent. But yes, question, Megan.
What's an arbitrary?
Arbitrary, I think of it as not random, but that's kind of how I think of it. So arbitrary number could be any number in the domain. Yeah, arbitrary number, any number in the domain. Good questions. Please ask questions like that, because these are, I try to use the terminology that's not only in the book, but you see this terminology throughout the class. So you'll see arbitrary quite often. But we can also think of the domain as a set of all possible input values, and the range as the set of all possible output values. Okay, so this is not trying to make, with all of the wording, the idea of a function any more complicated for you, but again, just reviewing that terminology. So we know a function, you have an input, it's typically the x value, it's a value from the domain, it's an independent variable, and then you have your output value, which is typically a y value, that's in the range, it's dependent. So putting all of that together. And then we have the most common method for visualizing a function is the graph of the function. So if f is a function with domain A, and then its graph is the set of all ordered pairs, this would be how it's written in set builder notation. So what this means, this ordered pair x, f of x is just y. So it's just an ordered pair x, y. We've kind of talked about this with the warm-up. So that vertical bar, you read that as such that. And then this would be x, this weird-looking e is element of. And then A was the domain. So it's basically saying for a function, the graph is made up of all ordered pairs such that the x value is in the domain of the function. And then this is just, I know can be wordy, but the graph is giving us the picture, a useful picture of the behavior of a function. We can also think of, it says in here, since the y-coordinate of any point on the graph is equal to the function value, we can read the value of f of x from the graph as being the height of the graph above the point x. So perhaps not right away, but at points in this class, there's certain times where you might be looking for the height of a function, and so knowing that that's just the y value at any given x value. But like I said, the graph gives us a nice picture of the function. All right, so that's mainly terminology. On the back, before we get to the examples, so 4 possible ways to represent a function, and you will see all possible representations throughout the course. So one way is verbally. So if you want to add to that, so a description in words. And then another way to represent a function is numerically. And this would be a table of values. So at some point in your graphing in your last 3-4 math classes, you've made tables to graph a function. And that table would be a numerical representation of the function. And then there's representing it visually, and that would be the graph. And the last one is representing it algebraically. So that would be if you have an explicit formula. That's always the nicest representation, is if you have a formula. So the idea here is that if we have one representation, we can maybe gain the other 3 representations. So if we have a graph, can we somehow get that formula maybe by using a table of values, and then we could also describe the graph in words, what's happening. So let's say I'm going to work from a formula and then kind of go up just to maybe add, make this a little bit more concrete. So say we have the function f of x equals the square root of x. That would be the algebraic representation. The graph of that square root function, so it starts at 0, 0, and then has that curve. It's steeper at the beginning and then kind of seems to level off. It is continually increasing, but it gets increases less and less. And then table of values would be if you had a table to represent that. So for the x value 0, square root of x is 0. For the x value 1, square root of 1 is 1. X value 4, I'll say, square root of 4 is 2. And then you could certainly describe what's happening with the graph of that function in words to have a verbal description. So you'll see all representations. And we'll also, thinking ahead, so say derivatives, you find ways to find a derivative of a function if you only have a table of values, if you only have a formula, if you only have a graph. All right, so this example that's here, I'm going to skip down, we're going to come back to example 1. We'll have time, I should have switched these. Go through the examples under example 2 first with finding the domain of each function. And I know this was covered in trig pre-calc, finding the domain from an equation. So reviewing here. So finding the domain. And again, try to write the domain in interval notation. So we have for a, f of x equals 2x minus 1, domain. Okay? It is an infinite domain, yes, all real numbers. What type of function is this? If you graphed it, what would it be? It is linear. We are going to go through, if you're looking at these and thinking what, we are going to go through all of the types of functions, what their formulas look like. So this is in the form f of x equals mx plus b, x is to the first power. It's linear. So that when you see an equation, the goal is, okay, I see that, I know it's linear, I can picture the graph, I'm working with a linear function. Just knowing that is helpful, which is why we have this first chapter. And the domain of every linear function is all real numbers. So typically in the past you may have just written all real numbers as the domain. So in interval notation you write that as negative to positive infinity. Infinity is always within parentheses, since infinity is an idea and not an actual value. Yes, b is quadratic because you have an x squared. And all quadratic functions have the same domain as well, which is what? That'd be the range. But they all, well, they don't all have that if it's shifted, but that would be the range of x squared. Domain, Yep, is all real numbers again, so negative to positive infinity. C, and I should have put f of x equals in front of it. Same for D. Typo on my part. Oh, you could put g of x, yeah, or h of x, or whatever you'd like. Type of function for part C, square root function. Or you could even just say it's a root function. Now, if it's a square root versus a cube root, there is a difference in the domain. So I'll say root, and this is even, an even root. So square root, fourth root, sixth root would all have the same, not necessarily same domain, but the same method of finding the domain. So anyone know the domain or know how they go about finding the domain of this particular function, Dalton? Okay, greater than that or equal to it, yes. So you could take whatever is underneath or inside of the radical, so x plus 2. Typically right away I just set it greater than or equal to 0, but you could just put it equal to 0 to find what that value is. So we know we can take the square root of 0 or any number that's positive. So that's why whatever is underneath, you want it to be either greater than 0 or equal to it. And then solve this for x. So if I subtract 2, all x values have to be greater than or equal to negative 2. So this, again, probably in the past would be a fine way to write it. You could certainly write set builder with this. So in interval notation, this would be negative 2 to infinity. We are including negative 2, it's greater than or equal to, so negative 2 has a bracket and then a parenthesis on the infinity side. So yeah, if it was an odd root, I'll write that at the bottom. That's a good question. Say it was g of x equals the cube root of x plus 2. Or at fifth root or seventh root. So if it's an odd root, all odd root functions have the same domain. And that's all real numbers, or negative to positive infinity. So odd roots, yeah, odd roots have easy domains. They're all positive to negative because you can have a negative number inside of an odd root. I can take the cube root of negative 8. It's negative 2. So that's the difference. Even roots, you'd want to find the domain using the method we used above. All right, and then for D, so this is a rational function. And the method for finding the domain of all rational functions is the same. Anyone know how you'd go about finding the domain of this function? Why is it called rational? So it's rational because it is a ratio of polynomials. And I know this part where I'm identifying the function, do I expect you to do that today? No, I'm just having you write it down. We will get to a point in chapter 1 where you are identifying the functions. So this is kind of skipping ahead, ratio of polynomials. Dylan.
All rational functions can be equal to 0, right? So
yeah, the denominator can't be 0. So a ratio, because it is a fraction, denominator cannot be 0. So in this case, we would say x squared minus x. This cannot equal 0. And then you find the x values. Basically, you're finding the x values that are excluded from the domain. So what can x not be? Okay. can't be 0, can't be 1. Did you just find those values by looking at it? Okay, so, and that's fine. How could I be sure, like, how could I solve this, I guess is what I'm asking. Yeah, so I could, this is solving a quadratic equation. There's a lot of review going on, I know. So solving a quadratic equation, I can factor out an x. So then I'd have x times x minus 1 cannot equal 0. Use that 0 product property. This means x cannot equal 0 or x minus 1 can't equal 0, so x can't equal 1. Okay, so then if I want you to write the domain in interval notation, so basically the domain is all real numbers except for 0 and 1. So how to write that? That means I can have every number from negative infinity up to 0, any number in between 0 and 1, and any number greater than 1. So I have 3 intervals. So how I would write that? Negative infinity up to 0, and I'm not including 0, so it gets a parenthesis. And then you use the union symbol, which just looks like a capital U. The next interval would be any number between 0 and 1, again, not including 0 or 1. So parentheses 0, comma 1, parenthesis, and then union again, parenthesis 1 to infinity. That one was more complicated, yes. Questions on that one though? So if say for right now, when you're practicing, if you're at least getting to the point where you know, okay, these values should be excluded, but you're still having trouble writing it, we can work on that. Right now, I at least want to know that you can identify what values are in the domain and then work on writing it in interval notation. The example that is above, for example, 1, I think I'd rather give you this last bit of time to work on this practice. I think if we go through this example tomorrow, it won't affect what I want you to practice tonight. So I'd rather give you time than take up every moment of time in class. So I'm going to stop.